when they're moving towards or away from each other, depending on the source or the listener. Okay. So the general equation is the frequency detected or heard by the listener is equal to the frequency given off by the source times the ratio of the speed of sound plus or minus to the speed of the detector or listener divided by the speed of sound minus or plus the speed of the source. Notice that I've left this area blank on purpose. They always have some plus or minus or plus signs. But what I like to do is look at it. So let's define each one of these terms first. I'm going to call these speeds because we only care about magnitude at the point, and we'll draw a picture to give us our direction. So this is speed of the listener or detector. Oh my God. Vs is speed of source. V is the speed of sound. This is the frequency from the source. And this is the frequency detected or heard by listener. Okay. So, really easy. Picture says 1,000 words for this. So here's your source. Here's your listener. Anything heading towards the listener is considered negative. Anything heading towards the source is considered positive, right? So imagine that the source is going towards the listener and the listener towards the source. So in terms of the signage we're going to put in, the speed of the source is negative and the speed of the listener is positive, right? And this is true. What happens when you have a source and listener moving towards each other? What happens to frequency? Let's think about this is the speed of sound in a medium. So let's say it's air, because that's how we hear sound anyway. So that's around 343 plus some number over 343 minus some number. Is that ratio greater than, less than, or equal to 1? Greater than, less than, or equal to 1? I need you to answer that. Is that ratio of V plus that speed of the detector or listener divided by V minus the speed of the source? Is that ratio greater than, less than, or equal to 1? Because that's all Doppler effect is. It's just a ratio. Yes, it's greater, right? Because it's 343 plus a number over 343 minus a number, right? So greater means what? Then you get a perceived frequency increase when you multiply to your original frequency. That's the perceived frequency change when things are approaching each other. That's that effect. Like if you ever sat down and watched NASCAR, right? And you hear that that NASCAR coming closer to you, it's that type sound that you have for Doppler effect. Because you hear that engine coming closer and closer, and it ramps up, and you hear that, and then as it goes away, it gets further and further away. So you get a perceived frequency change. It seems like it's happening more constant and more frequent when it's approaching you, and then when it goes away, those sound waves appear to be less frequent. Does that make sense? And that end overall effect is your Doppler effect in your system. Cool. So then what happens then if we change this? So now that the source is moving this way and the listener's moving this way, what happens to the signage inside of our equation? The speed of the listener and detector is positive or negative? It's moving to the right where the negative sign is. Nope, it's negative for the listener. What about the source? It's moving to the left where the positive sign is, right? That's positive. Negative for the listener, positive for the source. It's literally just following the picture, right? Anything going to the left, positive. Anything going to the right is negative. The better thing is to remember anything moving towards the source is considered positive. Anything moving away from the source is considered negative, the side that the source is on. Okay? So we get V minus some number. So 343 minus some number over 343 plus some number. Is that ratio greater than, less than, or equal to 0? I mean, equal to 1. Greater than, less than, or equal to 1. Less, right? Because you're going to take 343 minus some number over 343 plus some number. So that means it's going to be less than 1, which means the frequency that we're going to detect is going to be decrease. So the math behind this is really straightforward, but the understanding for Doppler effect is very real, right? Because this is what they use to catch you when you're speeding in your car. This is what cops use. They use Doppler effect, radar, or LiDAR. Radar is with electromagnetic waves instead of sound waves, and LiDAR, same thing with higher infrared type waves. Radar waves are kind of like the lower frequency waves, but LiDAR is what they use for higher infrared type frequency waves. They shine it at your car. They know their speed because they're the source, right? They know the speed of sound. They know what they're shooting out. They know what they're getting back. They can figure out what your speed is, the speed of the listener or detector, because they know this one, and this one, okay? And the speed of sound. Any questions? So equation-wise, speed of the Doppler effect is very, very straightforward and easy to remember. Any questions on that? Okay. Let's take a look at a question on it. Let's get rid of this one. So let's say we have a bat. It's the third question of the day. Is flying at 15 meters per second towards a tree. It emits a sonic chirp at 50 hertz. Assume speed of sound is around 350 meters per second. It's a really warm day, right? Because you think about it, where do bats live? Usually in the tropics. They don't live in cold weather areas. I want to know what frequency does the tree detect? And I want to know what's so funny? You think of real bats, right? You're thinking like those vampire fictional bats. I'm thinking of real bats, right? Where do actual vampire bats live? India. They don't live in Transylvania. Get out of town. You've been reading too much like you're reading too much Mary Shelley and Bram Stoker's. What frequency echo does the bat hear? It's really scary. Those vampire bats that you see migrating when you're like traveling in India or like Malaysia. They're scary. No joke. Like it's a sea of bats. You think they're birds until you get closer. It looked like a whole flock of bird migrating. And you're just realizing those suckers suck blood. Whether they're from animals, yeah, they're that many. And I was just like, oh, that's some nice birds that are traveling at sunset. And they're like, those aren't birds. Those are bats coming out to feed on the insects. And my guide's like, maybe we should get back inside the huts. Hey, they're keeping the insect population down, right? Because, with global warming, insects are going to keep on spawning. That's the one thing that's going to grow a lot with all this global warming. Every other like large species is going to die off, but like little species like that have short reproductive cycles that can keep on reproducing very, very fast insects are going to explode. So they do play a role in population control for those insects, keep them down. So I'm good as long as they don't suck my blood or the cattle's blood or whatever animal that's outside and their blood. So yeah, it's pretty freaking scary. Those things are huge, especially when they expand their wings out. Anyway, back to the bat question. So obviously bats are blind. They fly with echolocation. So them emitting a chirp emits sound waves. It hits something and it bounces back. And it tells them that, hey, there's something there by the Doppler shift that they see or the perceived frequency that they hear. They don't really see it. They hear it. So they visualize things by seeing it through their ears, right? As that sound wave comes back and hits their ears, they know like, hey, there's something there that's solid. Maybe I should dodge it. So that's how echolocation works. And if you ever been spelunking and you go into a cave, that's why people always are like, echo, echo, and you can hear where the sound waves are and where they're reflecting from. So that means there's walls there, and where there's no sound waves reflecting towards you, you want to make your way to that path, right? Because the echo coming back usually means that it's a dead end. So just good rule of thumb. Hollywood lied to you. If that was the case, if you guys were expecting Grey's Anatomy for like your doctoral careers, I will. I'm sure that there's plenty of people that told you that's not the case already. Or The Bachelor as your dating life, that's not the case. So yes, rule of thing, don't believe in Hollywood. Oh no, that part is going to be true. This is going to be true at med school. People start dating. Sorry. Med classes are generally pretty small, so you're stuck with these people for a while, and so there's always gonna be dating, you know, misery loves company. So who relates to you better? Same people in your program. And then you're like, the more you see them, they're like, oh, they're looking more and more attractive. So remember, common goals. But yes, there will be love triangles, sadly. I hear about all the times from kids that come back in med school. They go in, they're like, oh yes. I had students that boyfriend and girlfriend got into the same med school. They were dating, and then all of a sudden they weren't dating anymore, and they were dating other people, but also in the same med program as them, like in their class. So it's a real thing. It's just not endlessly cycling like they do in Grey's Anatomy. Oh, because living it, Jonathan, you get your heart broken. That's why people watch it, because watching other people get their heart broken is much easier than you getting your own heart broken. Oh yeah, it's super awkward, Monica. Like they can't be in the same room because like I know you slept with her and I know you slept with him, and then it's like super awkward. Whoa. I just had a question for one of my former students, and I was like, whoa, crazy. Yes, it's super awkward. Like, no joke. Like, I can't stress enough how awkward it is. And that part is true. Okay. I think this is enough time for this problem. So the first part is we have a bat flying at some speed of 15 meters per second towards a tree that's staying still. The bat gives off sound waves. We know that the frequency of sound is 50 hertz that the bat gave off. That's F of S, right? So this is the source. This is the listener, right? In this case. So we know that frequency from the tree is equal to the frequency from the source times the speed of sound, which is, we told her, 350. The speed of the detector or listener, trees don't move, last I checked, right? The source is the bat, and the bat is heading towards the listener, so it's 350 minus 15, right? So we know that there's going to be a frequency increase already. So it's 50, so it's roughly 52.2 hertz if you actually do the math. Now what happens is that sound wave that hits the tree in the second problem, the tree now becomes the reflecting of that sound wave. And the bat now becomes the listener. This is the listener, now this is the source. This is still moving at 15 meters per second, okay? So the frequency that the tree detected is also the frequency that it reflects. So the sound wave that it heard is also the sound wave that it reflects back out. So the frequency that the bat is trying to hear at is simply the frequency that the tree heard times that ratio of 350. The detector or listener is now moving towards the source, so that's a plus 15 all over 350, and the source now is the tree. The trees don't move, unless you're talking about like Lord of the Rings or something like that. So what we end up seeing is that the frequency that the bat heard is going to be 350, so over 350 minus 15 times 50 times 350 plus 15 all over 350. So these will cancel out, so you'll get 50 times 350 plus 15 over 350 minus 15, which is roughly 54.47 hertz. Okay, So the numbers I'm not worried so much about the numbers, but what I want you to notice is that when things are approaching each other, so when you have approach of the source of a sound and the listener, the frequency emitted is less than the frequency detected, which is less than the frequency echo. The echo is that sound wave that hit it and bounced back. Okay? So this is the echo. The bat is the echo. The tree was the detected, and the emitted was the 50 hertz in your problem. Okay? Any questions on that? But this is how you go about doing the problem for your Doppler effect type questions. Any questions on this? Okay, I kind of want to show you guys a cool video on sound visualization. I don't know if I showed it you guys during the lecture that we did on sound waves and waves part of this the lecture, but I think the kids who stayed for office hours got to see it. But I think this is really cool to see sound being visualized in 3D. Okay, so I'm going to share my screen. So let's take a look at our Rubens tube. Right.
Other tissues can cause a sore red
Go
nose.
through
Try Puffs, the #1 lotion tissue to soothe your blows.
Go through some commercials real quick.
Get your TV together with DirecTV Stream.
Yeah, go for it. Whoa!
Now you may have seen a Rubens tube before. That's basically a pipe with a bunch of holes in it, and you pump in a flammable gas and light it on fire. So you basically create a row of Bunsen burners. What's really cool is to play some sounds into the tube, and you can actually set up standing waves. That is, there are areas, there are patterns of the vibration of the air where there's a lot of vibration in some parts and not very much vibration in other parts. Now that affects the flow rate of the gas inside that tube into the atmosphere, and so it affects the height of those flames. So basically you can visualize the standing wave pattern. I'm currently in Denmark with a team of physics.
So that looks like superly overly photoshopped, but this one isn't. This looks like some dude that's literally in his garage doing this like same experiment, and you'll get to see the visualization as he pumps in regular sound.
Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So, what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. Alright, as you can see, we got some nice standing flames, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there and see what happens. Let's start with a 449 hertz frequency. As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is we're having the sound compressing here and not compressing here. The lower pressure here allows more gas to escape into the atmosphere, shaping the sound curve. Now, if we change the frequency, we can see each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck? Now we we have real life sound visualization with 5. The JP Rec isn't terribly energetic, so let's try something a little more energetic.
So we can clearly see that it's pretty cool to see sound visualization. Crack science experiments. Yeah, like that just like as a dude like in his garage like doing it, right? So like that other one, it was like overly produced and you can see it was like Photoshop. But what I wanted you to see from that video is how those molecules move parallel to wave propagation, right? So as it does this, that's what the sound wave is doing. It's propagating down the way. And the molecules move back and forth, compressing into regions of high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. And that's what causes the resulting sine curve or the wave. What I also wanted you to see is that when that dude was cranking it, you heard the frequency change, but not every frequency resulted in a standing wave for that fire that you saw in the Rubens tube. So remember, those resonant wavelengths, resonant frequencies are very high frequencies, very high wavelengths to get to those resonant wavelengths and resonant frequencies for sound resulting in a pipe. Okay. Same thing with those standing waves on a string, like the waves on the water surface. Those resonant wavelengths or resonant frequencies are very high energy, high frequency waves that only results at those specific frequencies within the system. Okay. Another thing that's cool, I want to show you something, one last thing for sound, and then we'll do our passage of the week. We're going to look at resonance. This is cool. Let me go back to sharing screen and making sure that I shared screen. So you don't see those. You don't need to look at the commercial.
Shockwaves from a punch can do damage to the human body. Now we're going to time warp at 10,000 frames per second to see how sound waves destroy.
By the way,
glass.
this is how sound waves break gallstones or kidney stones in your
Jamie
body.
Vandera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode. But what's happening?
I know the sound waves broke the glass, but I couldn't see how. So I'm going to use our slow motion camera to see what we were missing. Instead of singing, I'm going to use a speaker and a tone generator. I have to find the natural vibrating frequency of the glass. I have to match this tone. That's it.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw, then it's more obvious.
So what's happening here? The straw gets tossed side to side, but I can't see why.
Let's record it while I crank the volume. I took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Wow. So, as we would expect, the speaker breaks the glass nearest to it. And immediately we see a crack that goes all the way around the whole bottom of the frame. I'm going to play that back again. This is where the initial fracture happens, right nearby the speaker. And in about 3 frames, and this is 3/10,000ths of a second, we see this crack go along the bottom where the glass gets thicker and come right back up to the top where it's thin. So if we follow that a little more, this piece has just fallen off, but it doesn't in some sense even know that it's fallen off from the rest of the glass. All of the glass was shaking at about 300 hertz, 300 vibrations per second. And this piece is still doing that. You can see the corners of the glass still flexing as if they were influenced by the speaker, but the speaker is way too far away now to have that influence on this piece. It just has the leftover inertia. And we see that in all the pieces here, even along the top edge of this glass. This piece of glass is not resonant at that frequency anymore, so it can't get energy from the speaker, and all that we see shaking is the leftover energy from what the speaker gave it in order for it to break.
So, if you thought that glass couldn't bend, think again. Time warping changes the way we see the world because it makes the invisible visible.
Cool. Hopefully that opened your guys' eyes to like actual sound waves being able to do real damage to you, especially if you're going to like a concert or anything to that nature. Okay. So make sure that like you put in your earplugs and protect yourself when you go to those concerts because sound waves do real damage. So just keep that in mind. All right, let me pull up the passage of the week and then we will get started on it. Any questions from what we talked about today? Okay. Good. So hopefully you guys got a better appreciation of the sound and how sound can be visualized and captured so that you can see it and from those experiments that we just went over. All right, let's give you guys your passage of the week. There are 6 questions. I'll give you guys 7 minutes. You guys may begin. 1 minute warning before the end. You guys have a minute? Right, that's enough time. So let's give you the answers. So for those who have to leave, they can leave. And then if you want to stay for going over the problems, we'll do that after. Number 1 is C as in Charlie. Number 2, C as in Charlie. Number 3, B as in bat. Number 4, A as in alpha. Number 5, B as in beta. And 6, D as in delta. Okay. Okay, so any questions? Hopefully everyone did semi all right, but let's go through the answers. So we know a bug and bat are 17 meters apart. So we got the bug and then we have the bat, right? The bat. They're 17 meters apart. So if sound were projected and they were staying still, would go 17 meters there and then 17 meters back. So that'll be a total of 34 meters is the total displacement that you'll have to cover. And then that's equal to velocity times time, right? And we know the velocity is roughly 340 because 0.5 is going to add diddly to that, right? So time is roughly going to be 334 divided by 340 or 1/10 of a second. So that's if there was no movement between the bug and the bat, if sound was just being projected between them. The fact that the bat is the creature approaches at a relative speed of 0.5. So let's say bat is staying still and bug is approaching it, right? This makes it easier in terms of like your Doppler shifting. But what you realize is that that time that we estimated, or it's going to be 1/10, slightly less than that, right? So the one answer that makes the most sense is answer choice C from that. Number 2, this is using that sound intensity level equation. So we know that I is equal to P over 4 pi r squared. And we know that beta was equal to 10 times log of I all over I naught, right? So we know that when R is 1, right? 10 times log of power divided by 4 pi over I naught, that's equal to 25 decibels. So what happens is R is 2, so that becomes 4, right? So you're basically going to subtract log 10 of pi over 4 pi times 4 all over I naught. And we can rewrite that as 10 log of pi power over 4 pi divided by I naught minus 10 log of 4. So we know this is 25 decibels. Log of 4, well, that's log of 2 squared, right? So log of 2 plus log of 2 times 10. So we know log of 2 times 10 is 3. So we're subtracting 6 decibels, giving us 19 decibels. Answer choice C. Okay, so get comfortable with that for like these questions that you have for number 2. Number 3, a bug approaches a stationary bat. Any questions on those? Nope, good. A bug approaches a stationary bat at 0.01 the speed of sound. So 0.01 the speed of sound, that's 0.34 meters per second, right? Divided by 100 is 3.4. 0.1 of that is 0.34. So that's really slow. If the bat emits a sonic chirp at some ultrasonic frequency, the reflected frequency will be, right? Ultrasonic is above 20,000. So you don't even have to guess, like this is going to be really close to like the same frequency that was emitted. It's just going to be very little change because that speed at which the bug approaches the bat is going to be very, very small. Number 4, when a wave travels from air into water, its speed increases by a factor of 4. Compared to the wave in air, the transmitted wave has the same frequency and a what? Shorter or longer wavelength? It's going to be longer, right? Because remember, V is equal to lambda F. If frequency is the same, and we know that the speed increases by a factor of 4, then the lambda has to be increased by a factor of 4 for number 4. This goes back to the waves lecture when I talked about speed of a wave is simply the wavelength times its frequency. All of the following play a role in echolocation when determining position and speed of an object. A difference in frequency between the emitted and reflected waves. That's definitely true. A difference in wave speed between the emitted and reflected waves. There's no difference in wave speed. The speed of the wave is in the same medium. Marissa said earlier that as long as you're in that medium, it all should be the same speed. So definitely not. So this is an except, so we're choosing that as the best answer. Speed of the object matters, the difference in wavelength between the emitted and reflected waves. Same thing as saying difference in frequencies for number 5. So A, C, and D are all true. B is not. And the highest reflected frequency is observed when objects are both moving towards each other, right? And the only one in that case is answer choice D. Okay? Cool. Any questions? All right, with that said, we are done with sound and the Doppler effect. If you guys have questions, feel free to shoot me an email here on Thursday as well. Remember, Thursday, yes, I'll show number 3 again, A-Lot. Thursday is from 12 to 2. People were forgetting. Some people came in like 11, and I wasn't like at home to get online. So, yeah, just so you know, it's from 12 to 2 Pacific Standard Time. Thank you. Let's go back to 3, since A-Lot wanted to see. Cool. Number 3. A bug approaches a bat at a stationary bat, right? So the speed of sound, if the bat emits a source. So the bat is the source, right? And the bug is the listener. So this is your bug. This is your bat. So an ultrasonic frequency is something that's above 20,000 hertz. right? And the bug is approaching at so a speed of 0.34 meters per second, right? Really slow. So if you think about it, the frequency that the reflected frequency, the reflected is simply the frequency emitted by the source, which is 20,000 times they're approaching speed of sound plus the speed of the bug all over speed of sound minus the speed of the bug, right? So you think about it, 340 plus 0.34, 340 minus 0.34, that ratio is going to be really close to 1, right? It's hardly a change. And then you're multiplying it by the same frequency, so it's roughly going to be roughly a little bit more than the 100%. Does that answer your question, Neela? Cool. That's where it's from. Sorry, I just assumed that you guys were using that equation, so that's why I wanted to show you. So 0.1% of something is 1/1000th of it. So 340 is the speed of sound, so 1/1000th of that is 0.34. That's where that came from. Cool. Any other questions that you guys wanted to go over? All right. Thank you so much. Don't believe everything in Hollywood. The drama is real, though. So, yes. Take care, guys. Have a good week. You don't live in LA, right, Jonathan? You do. Oh no. Oh my. That's probably why you grew up with like everything is rainbows and unicorns around Hollywood, right? If you get a chance, Netflix, they have a pretty good episode of what like my friends tell me it's like for actors on like it's an episode. If you guys know Friends from Joey from Friends, like there's the series is called Episodes. Hilarious. It just shows you like the undersided seedings of like the whole like TV world. Yeah, it's called Episodes. I like it. It's pretty dark if you think about it. It's super dark about like Joey's life after like Friends and everything. So it's pretty cool. Yep. Have a good rest of your day.